Okay. All right, so we're going to start the method of undetermined coefficients. Let me talk about the grand scheme of things. We were trying to approach differential equations that look like the following. And we figured out that if you can just come up with one particular solution, just by guessing, I mean, I don't care what you do, if you find this one particular solution, then the general solution y is complementary solution plus the particular solution. Where this complementary solution was the solution of this left side equal to 0. That was the plan. Right? So basically we spent maybe 20 or 30 minutes last time trying to see that this is indeed true. Okay? So today's goal is to somehow come up with a streamlined way of finding this particular solution, because finding the complementary solution is easy. You just solve the characteristic equation and solve. That's the easy part. The YP is the hard part, so we have to figure out a streamlined way to do this. Okay. All right. So example 1. Let's try y double prime minus 2y prime minus 3y equal to, let's try e to the 7x. Let's just put 5, or something like this. Now, how would you find one particular solution that will solve this? Well, think about it like this way. If you have e to the 7x, differentiating once or twice will always have this e to the 7x with some coefficients, right? So if you plug this into the left side, it will be something times e to the 7x. Do you agree? And we need that to equal to the right side, and we just need to figure out what should be in here so that when something appears, those two multiply to create that 5. So the idea is to say, well, looking at the right side, it looks like if I try e to the 7x with some unknown coefficient as my yp, I can probably be able to figure out what this a is once I plug into the left side. That scheme is called method of undetermined coefficients. Okay? So let's see. Yp prime is 7a e to the 7x. Yp double prime is, another 7 comes down. Why did this 7 appear? Because of the chain rule. Right? The inside function has to be differentiated. 7x prime is 7. That has to be multiplied, so that's where this 7 is. So every time you differentiate, 7 will come out. So it's 49a e to the 7x. And then you plug them in here, which gives you, let's see, 49 minus 14 minus 3. Right? What's that? So it's 49a e to the 7x minus 14a e to the 7x minus 3a e to the 7x. Okay? If I plug these three things in the left side turns into this. Now, as you can see, a times e to the 7x is common, so let's factor it out and try to write down what we have. 49 minus 14, which is 35 minus 3, is 32 a e to the 7x. And I want this to equal to what? Want 5 e to the 7x. Now, e to the 7x, e to the 7x, good. Yeah, the hard part matches. The easy part is that 32a has to equal to 5. So what's a? 5 over 32. Putting that back into our original particular, we see that yp must be 5 over 32 e to the 7x. And then to finish off this problem, we need to find yc. What's yc? Yc is when you delete the right side and put 0 there. So you have y double prime minus 2y prime minus 3y equal to 0. R squared minus 2r minus 3 equal to 0. R minus 3. So that gives you e to the 3x as one solution, e to the negative x as another solution. Therefore, the linear combination is the complementary solution, c2 e to the negative x. And then you add this over here, so it's plus 5 over 32 e to the 7x. That's your y, okay? Where this much is yc, and this one is yp. Do you have any questions? Any questions? Yes?
Where'd you get the e to 3x and e to negative x?
Oh, yeah. So if you solve this one, what are the two solutions?
R equals 3 and
R equals to 3 and negative 1, right? And when we are solving constant coefficient homogeneous second order differential equation, the method was to solve the characteristic equation and put these numbers as e to the ax. So this e to 3x and e to the negative 1x. That's where these complementary solutions came. Any other questions?